So today I'm gonna be presenting another beautiful article of Christopher Manning, and which is called 3 LSTM. So this article is really interesting. So if you like this article with high probability, you also like this article, long short-term memory over tree structures. And this is really amazing article because you need it in parsing. You need it in parsing. You need it in different NLP task or even in computer vision. You can use it. So the motivation is that the only underlying LSTM structure that has been explored so far is a linear chain. This is the LSTM that we use. We are comfortable to work with that, and we think that is good. But in the world of parsing or in the real world, everything is like a graph. So that's why we need to have a better natural representation. Even in our brain, everything is connected like this. It's like a tree that we use. So we do parsing, therefore we exist. So we Christopher Manning in his beautiful article introduced 3 LSTM, which is a generalization of LSTM to tree-structured network topologies. So it has many applications. 3 LSTM outperforms all existing systems in strong LSTM baselines and 2 tasks. For predicting, I will explain the code of semantic relatedness of 2 sentences, and also sentiment classification is simple, so I ignore it. So what is the task? We want to know what is the relatedness score of these 2 sentences, how much this one is close to this one. There is a beautiful line of research which is natural language inference, which works on entailment and contradiction and neutrality and those things. I will explain it in a different playlist. And especially nowadays, the Allen Institute has created very beautiful data sets for natural language inference. That article about entailment tree, if you read that article. So every year we have a same eval workshop that we see what is the we evaluate different models and semantic meaning of that. And so as I said, we can have 3 categories: entailment, contradiction, neutral. So this is for task 1 of SEM eval 2014. I don't know what is the SEM eval of 2023. And so the architecture is like this. The top is one. Everybody knows this. This is just a simple chain, LSTM. But the bottom is quite new. So in 3 LSTM, we are working on that. So our hidden state or cell state is just the children of that. It has 3 hidden states and 3 corresponding cell states. So when you want to implement that, we take it into account. So we have a tree object. We add child to that. You can easily implement it. So this is a tree structured, and the way you can do that, if you don't know, if you have not fixed the number of children, you can use this module. But if you fix your number of the children, we say, for example, binary, all of them each parent has 2 kids, 2 children, and so on. Then you can use the n-ary 3 LSTM. And so the 3 LSTM, so we have 4 gates, but for k of them, because we have k children. And for child sum, as I said, you just add, because if you have 3 children, then you add the hidden states. So you add the hidden states of all of them, 1, 2, 3. So we have 3 kids, 3 children. And the same thing for output gate, forget gate, input gate, cell state, and hidden state. So let's implement child sum trees. You're implementing it, the forget gate, F here. You're implementing the output gate. The cell state, you see, It's just a multiplication of input and u, and then you sum with fc, and for fc we multiply f and child, and finally you get the h, which is multiplication of output and tan h. But child h sum is the sum of the all child h. So you return not only the cell state but also the hidden state for each node, of course. But here you gather everything, and you for forward, as I said, you know the tree, you know the inputs, so you know what is the tree state of that. You concatenate, here you get the node forward that I explained, node forward. So you use this because for each node you can see what is the returning cell state and hidden state. So once you know that, you know the tree state because you do it for all nodes of the tree. So return the tree, and so you can use it for dependency tree. So child sum is good for dependency trees because each parent could have many dependencies, many children. But if you are fixing it and say you have a fixed n, then your branching factor is n and you cannot improve it, then you can use this. So it's almost the same. You have forget gate, and you can use it for, this is good for constituency parsing if you're fixing it and you have using n-ary instead of children. And finally, we can use it for classification. Everything is standard. But let's implement semantic relatedness of sentence pair. So as I said, there are two different ways so we are creating these features, -1 or multiplication of them, because these are good. Each of them has its pros and cons. That's why we use both of them, h plus and finally h of s take advantage of these two features. And finally, we can say what is the for example the rank of that. This technique we use, for example, they're related from 1 to k different let's say score that two sentences could be related. And finally, we want to minimize the KL divergence between PK and P, and we do in machine learning use regularization. And this is another application, sentiment classification. But let's focus on sentence relatedness. For example, two sentences could be related if they have a high score. As I said, 1 to k. K could be, for example, 7. 7 is the highest score of relatedness of two sentences. So the similarity is very simple. So you first do embedding in child sum, and this is the initialization. For forward, you say, once you have embed the left input, left sentence and right sentence, and you give it for each of them, you give it to that child tree LSTM. Because there are two different inputs, so we have different outputs. And we get the similarity between left sentence and the right sentence. And this is how you calculate the similarities. So you need this H to have, as I said, we have two different features. And finally, you get the softmax of this WH, which is just a linear, it's just a linear model, linear layer. This linear layer, and you add bias, and finally you multiply it with this R. And that's it.